Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on December 18, 2025, so about 2 days ago. This paper introduces a unified stereo dataset called Uni-Stereo and a fast feed-forward model called StereoPilot that skips explicit depth maps and slow diffusion sampling, yet still beats prior methods in quality and speed, converting an 81-frame clip in about 11 seconds on one GPU. The paper is titled StereoPilot, Learning Unified and Efficient Stereo Conversion via Generative Priors. And as we will see later, the way it handles both parallel and converged stereo in one model is surprisingly clean. On Hugging Face, you can grab the StereoPilot Safe Tensors weights, plus the WAN 2.1 T2V 1.3 billion base model, and follow sample commands to run video to stereo inference. Figure 1 explains why depth-based stereo conversion can fail in reflective scenes because one pixel can correspond to two real depths. The full figure lays out a mirror example and then compares disparities, which are the left-right pixel shifts that create the 3D effect. The top row shows the ground truth-right view, a depth warp in-paint result, and the method here. The bottom row highlights that the depth warp in-paint disparity is wrong inside the red box, while the proposed result stays closer to ground truth. Figure 2 shows why stereo geometry is not one size fits all, so a depth warp shortcut can break depending on the camera setup. The full graphic contrasts parallel and converged stereo, and disparity means the left-right pixel shift that creates the 3D effect. In the left parallel diagram, disparity stays positive and follows a simple inverse relationship with depth. On the right converged diagram, a zero disparity projection plane appears, so disparity can be positive or negative. Figure 5 shows how StereoPilot trains a single model to predict the missing stereo view while staying geometrically consistent. The full diagram lays out two directions, left to right in blue and right to left in orange, which share the same idea of encoding a video into latents and running a transformer. The domain switcher is a small learned signal that tells the network whether it should behave like parallel or converged stereo. The cycle loss pushes left to match the original, so errors do not drift. Figure 6 shows that the model produces a right view that lines up better with the ground truth, especially in tricky regions where depth-based pipelines tend to slip. The full grid compares converged stereo on the left and parallel stereo on the right, with colored boxes marking mismatch areas. In the converged close-ups, faces and shoulders stay sharper and less ghosted. In the parallel examples, moving people and edges keep cleaner geometry, which matches the higher PSNR labels. Table 1 makes the core claim concrete because it shows the method winning on quality and speed across both stereo formats. The full table compares metrics like peak signal to noise ratio, which measures pixel level fidelity, and learned perceptual image patch similarity, which tracks perceived similarity, not just exact pixels. The stereo 4D parallel block shows the strongest scores in the StereoPilot row, including a peak signal to noise ratio around 27.7. The 3D movie converged block shows the same pattern, and the latency column highlights about 11 seconds per clip. Alright, two takeaways stand out. StereoPilot shows that you can skip the brittle depth warp in-paint pipeline and still get high-quality stereo by turning diffusion priors into a single feed-forward prediction. It also shows that a unified dataset plus a simple domain switcher can cover both parallel and converged stereo in one model. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.